In this video, we're going to use the integral test to help us determine whether or not a series converges or diverges. And remember, to use the integral test, we must show that our series function satisfies three criteria. And that's where we're going to start right now. So in order to use this test, we need to look at what our series function is first, which in this case is f of x is equal to 2 over the square root of 5x plus 1. Essentially changing all the n's from our series into x's, so we can think of it as a more continuous real variable, if you will. And now we need to show that it satisfies three things. The first thing is that f of x is positive. And in this case, we can really look at this function and ask ourselves if there's any x values that we put into it for x values greater than 1. Are there any x values in which this function is negative? And in this case, for any x value we put into it, it's going to be a positive valued function. So this is more or less, we can argue that it's positive. The second thing that we need to show is that it's continuous. And for continuity, what we're really asking ourselves is, well, if we put any x value from 1 to infinity inside of this function, are we going to get a divide by 0 anywhere? And in this case, the only way we would get a divide by 0 is if x is, well, something negative in this case. So in this case, it's continuous. We don't have any divide by zeros. Now, this last criteria is that it's decreasing. And we're going to do a little bit of work to show that this this function's actually decreasing. And remember, in order to show that a function's decreasing, we can take its first derivative and show that it's always negative on the interval that we care about. In this case, we care about for x values greater than or equal to 1. So let's relook at this function. We have f of x is equal to 2 over the square root of 5x plus 1. And I'm going to rewrite this into a different way, just basically taking that square root and putting it in the numerator by more or less changing the power to a negative value number. So we have 2 times the quantity, 5x plus 1 raised to the minus 1/2 power. And the reason I'm going to do that is so I can just in a more straightforward fashion, do a power rule type differentiation with a chain rule. So if we go ahead and differentiate this function, notice that this is the product of two things. We have this 2 times this other negative 1/2 powered thing. And well, if we differentiate a constant, it's just 0. So we don't really have to do a product rule here, but we actually will do a chain rule. So we have 2 times, bringing this minus 1/2 down in front. And then we multiply that by that same quantity, 5x plus 1, but now raised to the minus 1/2 minus 1 power, or the minus 3/2. And we multiply then by the derivative of what's inside, which in this case gives us a 5. So the overall derivative for this function takes the following form. We have a minus. We see the 2's cancel. We have minus 5. All times this quantity, 5x plus 1 raised to the minus 3/2, which we could equivalently rewrite as minus 5 all over the quantity 5x plus 1 raised to the 3/2 power. And now if we take a look at this, any x value that we put into that denominator, that quantity is always going to still be a positive number. So really, the thing that's making this entire derivative negative is the fact that in that numerator, we have a minus 5. So in this case, this derivative is always going to be negative for any x value greater than or equal to 1. All right, so in this case, we've checked that this function's also decreasing. So now that we've shown that this function satisfies the three criteria, we can actually go ahead and apply the integral test. And remember, the long and the short of integral test is we put the question of convergence or divergence onto an improper integral. If the improper integral is finite, the series converges. If the improper integral is an infinite quantity, well, then the series diverges. So what the improper integral does, the series does essentially. So let's go back and now apply the improper integral. So we'll take our series function, that's the function 2 over the square root of 5x plus 1. We integrate with respect to x, and we're going to integrate now from x equals 1 to infinity. And remember, where this x equals 1 is coming from is that's because our original series starts off at n equals 1. Now, with any improper integral, the first thing that we see is, well, we have an infinite integration bound. So we're going to introduce a limit to help us take care of that infinite bound. So we'll have a variable c that will take the limit as c goes to infinity of our integral from 1 to c now of 2 over that square root. And from here, once we've introduced that limit, we would proceed with the integration as we normally would. So from here, we can ask ourselves, can we integrate this with a u sub, integration by parts, going through our laundry list of different integration techniques? And well, for this problem, we can actually get away with a u substitution. If we let u equal 5x plus 1, we get du dx is equal to 5, which tells us that du over 5 is equal to dx. So we can substitute all of these quantities into our integral. Again, leaving that limit as c goes to infinity out in front. So our integral from still x equals 1 to c, we now have is 2 over the square root of u times du over 5, which was originally our dx. So from here, we can go forward with the integration. So we have this as the limit as c goes to infinity. I'm going to pull this factor of 2 over 5 in front of the integral. We have from 1 to c. And now I'm going to rewrite this instead of 1 over the square root of u as a u to the negative 1/2. And I'm doing this so I can apply the antiderivative power rule. So we still have this limit as c goes to infinity. We have the 2 over 5, but now we're going to integrate this. So we integrate with the antiderivative power rule. We add 1 to that power, divide by that power plus 1 as well. So we'll get u to the negative 1/2 plus 1 over 1/2 plus 1. And then finally, we'll evaluate that at the integration bounds from 1 to c. And just remember, this is we haven't changed the bounds in terms of u, so that is still x equals 1 to c. So let me just rewrite the previous line, just doing a little bit of the arithmetic. So we have this is now u to the 1/2 power all over 1/2, and evaluating that from 1 to c. The next thing we can do is resubstitute in what's u was. Again, this limit is still coming along for the ride. We see that we're dividing by a 1/2 in this denominator. So when we divide by a fraction, we reciprocate and multiply. So that'll give us a 4 over 5 times what was previously u, but now our 5x plus 1. And that's raised to the 1/2 power. And then we're going to finally evaluate this at our integration bounds. The bounds, again, from x equals 1 to c. So let's plug in the bounds next. So we have the limit as c goes to infinity, 4 over 5 times, plugging in the first bound, which is c. We have 5 times c plus 1. And I'm just rewriting that as a square root. And we subtract the lower bound from it, the square root of 5 times 1, which is 5, plus 1, which is 6. So again, the second term that's equal to the square root of 6. It's just some finite number. And the only reason I'm pointing it out is the thing that will actually determine whether or not this series converges or diverges, or this integral, if it converges or diverges, is this other term, because this is the term with the limit attached to it. So if we take this limit as c goes to infinity of the square root of 5c plus 1, as c goes to infinity, what's underneath that square root is going to infinity. So what this looks like in my limit vision is the square root of infinity as c is getting very, very large. And if we're thinking about the square root of infinity, that's just growing and growing as we're increasing that limit. So this quantity goes to infinity, which means this whole series must be divergent because this limit is equal to infinity, which means the improper integral is divergent. So by the integral test, the series is also divergent. So I'll just write that conclusion out. The improper integral diverges. So by this integral test, the series also diverges.